In section 2.7, we will discuss cylindrical and spherical coordinates. The Cartesian coordinate system provides a way to describe the location of points in space. The Cartesian coordinate system, or also known as the rectangular coordinate system, or also the Euclidean, provides a way to describe the location of points using x, y, and z coordinates. However, some surfaces can be difficult to model with equations based on the Cartesian coordinates. Recall, in 2 dimensions, you used to use polar coordinates whenever you had cases that involve circles. Recall that for polar coordinates, we will define r as the radius or the distance between the origin and a point in space, and the angle theta that defines the angle between the x-axis and the radius r. So if you turn this radius, you will get a circle like this, and the radius of this circle will be r. The point is moving on the circle with angle theta. In this section, we will look at different ways to describe the location of points in space based on the extension of polar coordinates. Polar coordinates are used in 2 dimensions. We will extend this idea to 3 dimensions. So in this case, we're talking about cylindrical coordinates, which are useful for dealing with problems involving cylinders. Spherical coordinates are useful for dealing with problems involving spheres. For cylindrical coordinate system, we will define an ordered triple like r, theta, and z. R and theta are the same polar coordinates we already defined in other courses in mathematics. We will add a third one, which is the z coordinate, which is which is the one that is used in the Cartesian coordinate system. Consider a rectangular coordinate system, which is a Cartesian coordinate system, x, y, and z, and these axes are pointing in these directions. This point P is described as x, y, z in space in Cartesian coordinates. In cylindrical coordinates, we will define r, theta, and z. Let's transform a cylindrical coordinate system to Cartesian coordinate system. We will derive, we will make a derivation of 3 equations where you can interchange between the 2 systems. We know from any point in space in 3D, whenever we want to find x, y, and z, we will project on the x-axis and on the xy plane. And after projecting onto the xy plane, this is the xy plane, you project onto the x-axis to find x and y. This is the value of x. You can also project to the y-axis to find y. This is y, which is the same as this one. Since this is a rectangle, the parallel sides are equal. Now let's consider this triangle. After the projection, we will obtain a 90 degrees, which means this is a right triangle. The side of this right triangle is given by x, y, and r from polar coordinates, which is the distance between the origin and this point in the xy plane. Keep in mind that r is obtained after projecting onto the xy plane. There are a lot of misconfusion or misconception about r. You only get r after you project onto the xy plane. So let's find x and y from this angle theta, which is the angle between the x-axis and r. The angle theta now can be obtained from this right triangle. We will say that cosine theta is adjacent. This is the adjacent angle x, and this is the opposite, and this is the hypotenuse. So cosine theta is equal to adjacent x divided by the hypotenuse r, cross multiply to find x. X is equal to r cosine theta. For y, to find y, sine theta is opposite, which is y divided by the hypotenuse, which is r, cross multiply to find y will be equal to r sine theta. As for the z, you can directly project to the z-axis, and after the projection, like this, consider this, assume this is a straight line. I cannot do it with this pointer. Uh, we project, and this is a 90 degrees. The z coordinate for this point is given from the origin to this projection, or saying the same as saying from this point to this point. Both are z, since this is a, a square or rectangle, the opposite sides will be the same. So z is equal to z. Now, we can also uh, transform from rectangular to cylindrical. This is from cylindrical to rectangular coordinates. If you have the values of theta and r, you will get x and y. You can calculate x and y. Now, let's say you want to transform from rectangular to cylindrical. You have x, y, and z. From x, y, and z, I can calculate the angle theta and r. To find r and theta from rectangular coordinates, we can use this equation, which is given by Pythagoras theorem. R in this right triangle, r squared, the square of the hypotenuse is equal to the square of the second side plus the square of this third side. So this one can be easily calculated if x and y, or if you know x and y. Now, the angle also can be calculated simply by having the tangent theta. Tangent theta is opposite over hypotenuse, which means that it is y over x. For z equal to z in both transformations. Keep in mind that r is positive, this is a condition, and theta is between 0 and 2 pi. This is always the case. Example 2.60, let's convert from cylindrical to rectangular coordinates. Plot the point with cylindrical coordinates for 2 pi over 3 minus 2 and express its location in rectangular coordinates. So we know r, we know theta, and this is z. From the previous equations where you transform from cylindrical to rectangular, we're gonna use these three equations. Just replace r equal to 4 in both equations and take the angle 2.3. Replace and calculate, you're gonna get minus 2 for x and 2 radical 3 for y, and z is equal to z in both rectangular and cylindrical coordinates. This means that z is equal to minus 2. So the point with cylindrical coordinates with this one has a rectangular coordinate minus 2 to radical 3 and minus 2. Let's convert an example 2.6 from rectangular to cylindrical coordinates. Convert the rectangular coordinates 1 minus 3, 5 to cylindrical coordinates. Now, this is rectangular coordinates, which means that this is x and this is y and this is z. We know how to calculate r and theta. R by Pythagoras theorem is equal to x squared plus y squared. Now let's find r, which is equal to square root 1 squared for x, and y is equal to minus 3. Replace it here and don't forget to square and then add them. So r should be positive, so r is radical 10. For theta, tangent theta is opposite over hypotenuse, which is y over x. Just replace their values and calculate the angle of theta. Now for z equal to 5. So in both coordinates, rectangular and cylindrical coordinates, they are the same. Describes the surfaces with the given cylindrical equations. In this example, we have two equations, and we will describe what kind of surface is this equation. Is it a sphere? Is it a cylinder? Or any other type of quadric surfaces? In part A, you are given r squared plus z squared equal to 9. We know what is r. r is equal to r squared is equal to x squared plus y squared. Replace it in this equation in cylindrical coordinates. So replace in r, you will get x squared plus y squared, which is r squared, plus z squared equal to 9. If you look at this equation, we know exactly what is that. This is an equation that describes a sphere, and the center is the origin. You can see from here that the center is the origin and the radius is equal to 3. As for the second one, z equal to r. To describe this surface defined by equation z equal to r, sometimes you want to replace equations in other equations like we did now. Since we know we're working in cylindrical coordinates, we will replace, like, for example, r squared in the equation over here, or maybe you're gonna use another equation in the cylindrical equations defined by theta in the given equation in the example, and do some rearrangement or recalculation to find the final equation and know what kind of surface. Sometimes you need to use the trace. For example, we have z equal to r. So let's, for example, take z equal to 1. And we saw from previous lectures that z equal to 1 is a plane parallel to the xy plane. You can you can draw this online, and at x equal to 1, which is right over here, you can draw a plane like this, and um, you will get a circle. This is 2, this is 1. I think I drew it on 2. That's okay, not a problem. So the intersection of this plane with this cone will give you a circle. a circle of radius 1. Now, if you move this upward, you can try this online. If you move this upward, let's say z equal to 3, 1, 2, and 3 at this point, and you draw a plane, the intersection is also, or the intersection will give you a circle, also a circle, but a bigger one. Since the cone, as you go upward, as you can see here, it is getting bigger and bigger. If you draw a plane over here, you're gonna also trace a bigger circle as you go upward and so on. Now let's discuss spherical coordinates. In spherical coordinates, we will define this order triple: rho, theta, and phi. Rho is the distance between the origin and point P in space. Theta is the same as before. It is the angle between x and theta. As I mentioned before, don't confuse between r and rho. R is obtained whenever you do a projection from point B onto the xy plane. The result of this projection will give you r, which is the distance between the origin and the point on the xy plane. Rho is the distance between this point, the origin, and this point in space without any projection. Theta is the angle as before between x and r. Phi is the angle between the z-axis and rho. Theta is an angle that takes values between 0 and 2 pi, while phi takes values between 0 and pi. Let's find the equations that lets you convert between spherical to rectangular and from rectangular to spherical coordinates. Consider this point again in space. This is x, y, and z in rectangular. In cylindrical, it is given by r, theta, and z. In spherical coordinates, rho, theta, and phi. Let's derive these equations. Now, we know from the previous case that x over here, when we projected, let's say this is another straight line projected onto the x-axis, and we got this value of x over here. And we said that cosine theta is adjacent over hypotenuse, which means that we can cross multiply, rearrange the equation, and get x equal to r cosine theta. Okay, now we can replace in r to find x in spherical coordinates. Since we're working in spherical coordinates, we don't want r, we want rho. So we need to remove r or to replace it with another equation so we can write x in terms of rho and phi. From this triangle over here, because we have now a second angle in addition to the theta, let's take this triangle over here, the right triangle after projecting onto the z-axis. Now we know that this side over here is z, and this side over here is r, which is parallel to this side in this rectangle or square. So this side is r, this means that this side is r. Now, sine phi, this one, the sine of this angle is opposite, which is r, divided by the hypotenuse, which is rho. Cross multiply, we're gonna write r is equal to rho times sine phi. Replace an r over here, rho equal to sine phi, this one. And we already have cosine theta multiplied by cosine theta. So we're gonna write our first equation, rho sine phi cosine theta. Now, for y is this side over here, right? So we know that sine theta is opposite over hypotenuse, so sine theta is equal to y divided by r. Please do that, try it out, and use this uh, use this equation to find y. As for z, also try to find the, a relation between z and the angle phi in order to find this one. So these three equations will allow you to transform from spherical to rectangular coordinates. For rho squared, we know from before that we used the Pythagoras theorem, rho equal to x squared plus y squared. Now we can extend this idea. The Pythagoras theorem can be used in three-dimensional case, and all you have to do is to add z squared. So yes, this is Pythagoras theorem in three dimensions. So rho over here is equal to x squared plus y squared plus z squared. Again, you know from previous case that tangent theta is y over x and phi is this one. If you take cosine phi is z divided by rho, which means that phi equal to arc cosine of z over rho. Z over rho. Rho is given by this equation according to the Pythagoras theorem. So this kind of transformation, we go from rectangular to spherical coordinates. Okay. Now, we can also transform from spherical to cylindrical coordinates and from cylindrical to spherical coordinates. And we're gonna use the same concept as before, where we use these are very easy to find. R in this case is equal to rho sine phi. We already did this one using this equation. Theta equal to theta in both cases. It's the same angle in spherical and in cylindrical because theta in both coordinate systems is the angle between the x-axis and r, and z can be found from this equation. Okay, converting from spherical coordinates. Plot the point with spherical coordinates 8, pi over 3, pi over 6, and express its location in both rectangular and cylindrical coordinates. So we need to convert from spherical coordinates to rectangular coordinates in first case and to cylindrical coordinates in the second case. So from moving from spherical coordinates to rectangular coordinates, we're gonna use these equations from spherical to rectangular. All you have to do is to replace the values of rho, phi, and theta, which are given, and do the calculations. So you have this equation, replace rho, which is equal to 8, phi, which is equal to pi over 6, and theta, which is equal to pi over 3. Same thing for the other, for y and z, calculate, and you're gonna get these coordinates, these values, 2 radical 3 and 4 radical 3 for x, y, and z respectively, and these are in rectangular coordinates. Similarly, we will use these equations to convert from spherical to cylindrical coordinates. Again, just replace their values to calculate r equal to 4, theta is equal to theta in both cases, which is pi over 3, and calculate z using this equation, and you're gonna get the cylindrical coordinates for the point 4 pi over 3 for radical 3.